Okay, I'm going to go over with you one of my absolutely favorite motion problems. The reason it's my favorite, not only does it include pretty much every great thing that we have talked about, it's a practical scenario. This is something that actually could really happen, all right, where this data could actually be real. So we're not on Mars, we're not on the moon like we are in some of the other homework problems. This could have actually been a real life scenario. So again, I want to point out to you that we are looking at a velocity graph, right? That is so counterintuitive for us. Students often think the object rose till 2 seconds, then it fell all the way down here, and then it rose again. That's what many students think because they're thinking position, right? It's really hard to program your brain around the fact that this is not showing position. This is in fact showing velocity. Okay, so what we know about velocity is that when velocity is positive versus negative, right? That tells us something about the position of our object. All right, so before I ever even look at the questions, I want to think about when is velocity positive, when's it negative, and when's it zero, right? Remember what is significant about velocity equaling zero, right? Why is that significant? The derivative is zero, right? What significance does that have for the path of our object? But first of all, let's make sure we've read this. All right, so we've got a rocket that's launched and it's propelled. It has a propellant, right, that burns for a few seconds. So it starts off and it is accelerated, right? It has this extra burst of acceleration because it's got this rocket or this this propellant that is burning. Okay, so this burning accelerant burns out, right? So after burnout, so we have to consider when is it being propelled or accelerated, right? When does that then burn out? Okay, so after the burnout, it coasts upward a little while, and then it begins to fall. Okay, so we're going to be looking at where each one of these happen. All right, so it's falling, but as it's falling, then a parachute pops out, right, and actually slows the rocket down. So it's falling, but it slows. Okay, so keyword here is slow. So we're trying to look at, based on the velocity graph, when each of these things happened. Okay, now we have to remember that when we're talking about acceleration, remember that acceleration is the derivative of velocity. Okay, so A equals, for acceleration, dv dt, right? The derivative of velocity. And we're looking at a velocity graph. And so if I went along there and I put tangent lines along there and looked at their slope, I'd be finding acceleration. Okay, but first of all, let's come over here and notice that the velocity is positive from 0 to 8 seconds. Okay, I added in, you guys don't have this, but I added in, and I suggest you take a ruler and highlight here at velocity 0. All right, so that's highlighted. Velocity is negative then from 8 seconds until the end of the problem at 12 seconds. Okay, velocity is 0 at 8 seconds right here. Okay, so what does that mean? And so I've highlighted on here. I'm going to try to color code. That's where it begins to fall, right? So the object is actually rising from 0 to 8 seconds. It changes directions and begins to fall at 8 seconds, and then it's falling for the rest of the time. Okay, but as it's falling, suddenly it will be caught by the parachute, and begin to fall at a slower rate. Okay. Now the beginning of the path then, so we're rising from 0 to 8. So how fast was the rocket climbing when the engine stopped? Okay, so remember that engine that we start off with propels it, and it only burns for a few seconds, right? So where is this object really being accelerated? All right, and what we should be able to see is that the steepest tangent lines, right? The tangent lines to the velocity curve are the steepest through here, right? So right here in this section, we have velocity positive, acceleration positive, which means that we speed up, okay? Over here on this side, we have velocity still positive, but acceleration is negative, okay? Because the slope is negative. So we should recognize that over from here, from about 2 seconds until 8 seconds, what is happening over here is that we slow down. Okay, when velocity and acceleration have opposite signs, we have a slowing of our particle that's in motion. When velocity and acceleration have the same side, we speed up. Okay, so the burning engine caused us to speed up, right? Right at the beginning of our path, we accelerated. Okay, so it looks like this happens at about 2 seconds where we go from speeding up to slowing down. So notice we're still rising, right? We're rising until we get to 8 seconds, but we accelerated, right? Then we continued to rise after 2 seconds, but we started rising at a slower rate. Okay, so let's start actually answering some of the questions in the problem. How fast was the rocket climbing when the engine stopped? Okay, so the engine stopped burning right here when we went from speeding up to slowing down. And we count by tens. So this would be 190, and then units are important, right? So feet per second. All right, and that engine, that accelerant, burned for 2 seconds. Okay, the first 2 seconds, we are speeding up. All right, from 2 to 8 seconds, we are slowing down, although we're still rising. Okay, so then we go over here. When did the rocket reach its highest point? What was the velocity then? So again, it's so tempting to say this is the highest point, right? This 190. But remember, our highest point happens right here, right? When velocity is 0, when I change directions, okay? I have no way of knowing how high the rocket actually got. I can't determine that by looking at a graph of velocity, but I know that it reached its highest point right before it started falling, okay? So this is t equals 0, and what's the velocity then, right? When an object starts falling, the velocity at 0 seconds, right? V of t, V of 8 is equal to 0. Okay, the velocity is 0 when our particle or our object changes directions. Okay, so now let's start talking about the part where the object is falling. Okay, from 8 to 12 seconds, the object is falling. So right in here, I have velocity negative, right? Because we're down below 0, and the slope is still negative, which means acceleration is still negative, okay? When both of these are negative, that means right in this section that I speed up. Let's see, you can hardly see that. Let me try to move it down. Move my words down. No, they don't want to move down. Okay. They speed up here. Okay. So it's falling, and it begins falling at a faster rate because that's what happens when an object is in free fall, right? Because of the forces of gravity. As it falls, it begins to pick up speed. Okay. But then over on this side, we have velocity is still negative, right? Because we're still below the t-axis or the x-axis, whatever you want to call it. But now the slope is positive, right? And we know that when velocity and acceleration have opposite signs, they move in opposite directions. Right here, we slow down. Okay, so the last part of our path is slowing down. So that must mean that the parachute opened right here at about, it's really hard to tell, but let's say about 11 seconds. Okay, and how fast were we going? So let's go across. It looks like we're right here at negative 90 feet per second, right? When that happened, because we are falling. And how fast? So actually, if we're looking at speed, I won't use the negative. I will just put 90 feet per second. Okay, when that happened. And how long did the rocket fall before the parachute opened? This is feet per second. So it looks like we went from 8 to 11 seconds. So about 3 seconds. Again, we're approximating, right? So I'm going to do the approximately equals 3 seconds. And when was the acceleration the greatest? Okay, throughout this whole path. So remember that acceleration is the slope of velocity. When does this thing have the steepest slope? Okay, and if I look at the tangent lines that I'm drawing, right? I mean, here, this would model the acceleration. Acceleration's not super steep right here, but like look right before 2 seconds, right? That tangent line is practically vertical, right? So that would have a very large, that would be the largest slope, okay? Meaning that the acceleration is greatest just before 2 seconds, right? Just before that engine burns out. Okay, so just before 2 seconds. Okay, and when was the acceleration constant? And what's its value? Okay, so again, acceleration is the slope of velocity. Okay, when does this velocity graph have a constant slope? Okay, and all of that would happen where the part of the curve which is linear. Okay, actually let me mark it this way. I'll mark it like that, right through here, right? The slope is constant, therefore the acceleration is constant. So what is the value of the acceleration? So that goes from about 2 to about 11 seconds. So if we were to do slope along this curve, we know we have the point 2, 190. And we know we have the point approximately 11, 90. Okay, so if we were to find the slope, then change in y over change in x. So let's see, I have 100 over 9. Something's wrong. Oh, negative 90, right? So I actually, when I subtract, I get negative 280. There we go. That's the problem. The sign matters when I'm doing this. Negative 280, so this minus this over that minus that, which is 9. And we are on Earth in free fall, sorry. And so we would be expecting a number like 1 negative 32 feet per second squared. I got negative 31. Okay, and that's from just from estimating it. Technically, I got negative 31.1 feet per second squared. But we know if we're on Earth and something is in free fall, right, there is a constant of acceleration of negative 32 feet per second squared. Okay, so again, I love this problem because it takes into account so many of the concepts and skills that we've just learned about speeding up, slowing down, right? Velocity versus position versus acceleration and all that good stuff. So thank you for watching, and I hope this increased your understanding.